12.1 is a pretty big section of the book, and it really has three closely related but honestly different topics here. So I'm going to break it up into three different videos. It's quite possible you may find, like, I don't know, the first one and the third one are really easy, but the second one you find yourself having to watch over and over again, or something like that could easily happen since these three topics are each pretty different. So they're going to be three short videos rather than one long video. That way you can pick and choose which ones to watch. So this first one, we're going to be talking about a new idea called composition. And the idea is this is an arithmetic operation that's a new one. It's not adding, it's not subtracting, it's not multiplying, it's not dividing, it's not exponents. It's something brand new. And the reason why we didn't study any new arithmetic until now is all those other arithmetic operations, you can do those with numbers and with functions. This new operation you can only do with functions. You can't take two numbers and compose them, but you can take two functions and compose them. So let's talk about the notation first, and then what it means, and then do some examples. So the notation, it's easy to confuse it with multiplication if you don't pay very careful attention. That little symbol right there, that little circle thing, that is not a dot, so it's not multiplication. And honestly, it's not even a circle, although it looks a lot like a circle. It's much better to think of that as a little tiny sort of abbreviated letter O. The reason why you should think of it as the letter O is because it stands for something. It stands for the word of. So if you read this notation and you read that little O as the word of, then what you would read is f of g of x. F of g, parentheses, of x. And if you read these words here, these words translate directly into the meaning. So it's supposed to be a self-explanatory notation if you know what the little circle is. As long as you know that stands for the word of, f of g of x means f of g of x. And really kind of the only difference is when do you pause when you're saying things. Do you say f of g, pause, of x, or do you say f of, pause, g of x? It's the same thing either way. It means the exact same thing. So let's do an example because it still doesn't really make sense yet. Until you see it actually happening in an actual example, it's not going to click. So here's an example. We've got function f is 3x squared plus 2. Function g is 3x minus 5. Those are a couple of really simple functions. We're not getting fancy yet. Then, going from our definition, our actual, like, defining meaning of what this stands for, f, little circle g, parentheses x, that means f of g of x, so that means f of g of x. I'm going to try to color code it here to help you see what's going on. G of x is a thing that is getting plugged into f. And you know how to plug things into functions. If you're supposed to plug in for x in the function f, then that means wherever x is, plug in for it. So it's 3x squared plus 2. Well, where the x used to be, plug in what g of x is. Okay, what's g of x? Well, g of x is 3x minus 5. So what we're doing here is basically just plugging in, but there's something about it that seems weird the first few times you do it, because you're used to plugging a number in. You're not used to plugging an entire expression in like this. Although, to be honest, you probably did something very similar to this back when you were doing systems of equations. You would take one equation and solve for one of the variables, and then you would plug in for that variable in the other equation. You can think of this as sort of an advanced version of that same basic idea. So you're not done at this point, but you're pretty close to done. now all you have to do is simplify this algebraic expression you've created. So for example, this 3x minus 5 squared thing, probably ought to take a second and FOIL it out. So that's going to be, let's see, 9x squared minus 15x minus another 15x plus 25. So we're going to have 3 times all of that plus 2. I'll take a second and collect those 15x's, of course. Why not, right? Distribute in the 3. We got 27x squared minus 90x plus 75. Oh, wait, plus 2. I'm not entirely done. So my final answer here, f composed with g of x, comes out to be 27x squared minus 90x plus 77. So notice, this is not just 3x squared plus 2 multiplied by 3x minus 5. It's certainly not adding. This is not like any other arithmetic operation. And because it is an arithmetic operation, your brain is automatically going to try to think of it the same way you think of other arithmetic operations like adding and multiplying. And that can actually be kind of dangerous because you have a lot of intuition about how arithmetic works. And your intuition may very well be wrong here. For example, let's take a look at what happens if we do the composition in the other order. Because your intuition, your instincts are telling you the order shouldn't matter. Like 3 plus 5 and 5 plus 3 is the same. 3 times 5 and 5 times 3 are the same. The order shouldn't matter. But it turns out with composition, the order really matters. It's going to make a big difference. So here, read this thing off. G with the little circle in f and then parentheses x. That's g of f of x. That means g of f of x. And again, I'm going to color code things to try to help out. F of x here is a thing that's getting plugged into g. So to plug into g, we have to plug in for x, 3x minus 5. We got to plug in for x the thing that f of x is. F of x is 3x squared plus 2. And this is a lot quicker to solve for than the previous one. We don't have to FOIL anything out. We just have to distribute that 3 in. 9x squared plus 6 minus 5. And then there's a tiny little bit of collecting like terms, but not very much at all. And you end up with this, 9x squared plus 1. So take a look at these two answers. F composed with g and g composed with f, not at all the same thing. Really, really different from each other. In fact, if f composed with g and g composed with f came out to be the same, I'd be really surprised. I'd be like, whoa, that's weird. What happened there? That's a really interesting example. So if they ever do happen to come out the same, I guess it's possible, that would be kind of surprising. They usually come out pretty different from each other. Okay, now our next video is going to be about inverses of functions. It'll be related to this stuff here, but it'll go in a new direction.